So let's go
Recording
to
in
the next
progress.
Okay, so this is the formula that will be given to you during the finals. Okay, so you'll be given this formula. Only very little formulas here. So you have your linearization formula, your Newton's method, and your trapezoidal rule and your Simpson's rule. Okay, and then here you have your derivatives and your integrations here. Okay, these are the only formula that will be given. So no other formula will be given to you during the finals. So you will need to memorize all the formulas that you need. Okay. Okay, so let me start the question proper. So first question here, we have the point A and B have the coordinates 2, 6 and -10, 0. So 2, 6 is here. Then -10, 0 is here. Okay. Then they say a line passes through A and is parallel to AB, the vector AB. So this point is A, this point is B. The vector AB is this. Okay, this is the vector AB. Okay, so my line passes through A and is parallel to this vector here, meaning my line will be in the same direction and it passes through AB. So the line will look like this. So use your ruler, right? Use a ruler and draw a straight line that cuts through this. Okay, let me just try and... Okay, so you should cut through this point and this point. So this is the point L. Okay, so this first part, we should be done here. So we have point A, point B, and a line L. If you have any questions, just feel free to write in the chat. You write to everyone. Okay, I won't be checking the DMs because I'm on another PC. So you write to everyone, I can see the message. Okay, then for part 2, we want to find the length of projection of AO onto AB. Okay, so the length of projection of U onto V is equals to the dot product of U with V hat. Okay, with V hat. So let me just V hat here. Okay, so here I want the projection of AO onto AB. So AO, what's the vector AO? So the vector AO is from A, you're going to O, the origin. So this is -2, -6. Okay, then AB is equals to OB minus OA, OB minus OA. This is equals to -10, 0 minus 2, 6. Then you should get. Okay, so we have AO and AB. So let's go ahead and calculate this. So this is AO now, and this is AB. Need to extend L beyond AB. Yes, you need to extend the line L beyond the vector because the line extends infinitely. So if your line is only between A and B, that is incorrect. Your line should extend infinitely long. Okay, so your line cannot be just A to B like this. This is wrong. It should be all the way to the end. Okay, so go ahead and calculate this dot product. So take the dot product of U. U is -2, -6. Okay, dot with V hat. So we dot with V, so it's -12, -6. Then divided by the norm of V, the square root of 12 square plus 6 square. Okay, so go ahead and take the dot product. So here you should get 2460 over square root of, what is this, 144, 180, 12 square. I'm going to calculate this. Yeah, 180. Okay, so express your answer in the form A square root B. So just go ahead and express it in the form. So this is the same as saying 60 times square root 180. Square root 180. What is square root 180? 90 times 20. It's 9 times 20. So this is 60. Okay. So square root 180 is equals to square root. So right now all the is 9 times 20. Or maybe you should divide by 6. Maybe you should divide by 6. We can factorize it. 36 times 5 is 36 times 5. So this is 6 square root 5. Okay, and so this is 10 over square root 5, which is 2 square root 5. Okay, so that's for part 2. So you need to express this in A square root B form. Okay, so let's move on if there's no questions. Okay, so part B, let's look at part B. So O, P, Q, and R are distinct points such that OP equals to P, OQ equals to Q, OR equals to R. If R is perpendicular to PQ, Q is perpendicular to PR, show that P is perpendicular to QR. Okay, so here, remember that if two vectors are perpendicular, means that their dot product U and V is equal to 0. Okay, let's say U and V are perpendicular, then U dot V will be 0. Okay, so we have if R is perpendicular to PQ. Okay, so if R dot with PQ, PQ is something like PQ. PQ here is equals to OQ minus OP, which is Q minus P. Okay, PR is OR minus OP, which is R minus P. And QR is equals to OR minus OQ is equals to R minus Q. Okay, Q must be R must be. Okay, so here, so we can take the dot product. So R is perpendicular to PQ, means that R dot with PQ, which is Q minus P, is equals to 0. Then similarly, we have Q perpendicular to PR, Q perpendicular to PR. So here we will have Q dot with PR, which is R minus P, is also equal to 0. So here you can read, so here if you expand out, right, you got RQ minus RP equal to 0. Here you have QR minus QP equal to 0. Again, all these are vectors. Okay, I'm just gonna write down that they're vectors here. So here, I want to show that P is perpendicular to QR. So here in the end, what I want to show is P is perpendicular to QR. This is what I want to show in the end. We want to show this in the end. Okay, we want to show this. This is what we want to show. So if you show this, you're done. Okay, so here, to move on from here, you just need to have these two expressions. You just try and manipulate them. So here, notice that we have RQ and QR here. We can substitute them. So we have RQ equals to RP, and QR is equals to QP. Right? So we can equate RP and then write RP is equals to QP because RQ and QR are equal. So RP is equals to QP. Okay, so you can go ahead and what we want to show again? We want to show R minus Q. Okay, R minus Q. So we can move this RP minus QP equal to 0. Factorize out P. Yeah, R minus Q equal to 0. And this is the dot product of OR minus OQ, which is QR. So P dot QR is equal to 0, which means that P is perpendicular to QR. Okay, sure. Okay, you can stop here. Okay, any questions? If you have any questions, just feel free to write in the chat. Okay, doesn't seem like there's any questions. Let me move on. So expect one question for each topic before calculus. So you have one question on vectors, one on matrices, and one on complex numbers. Do we have to underline the vectors or no need? You should lah. You can write the curly sign on top. But I don't think will be that, depending on the marker. So if you want to play safe, you should. Okay, so you should write down all the curly sign. When this and this is that a question? When with and arrow. When with, when arrow. Arrow is when you got letters. Arrows is like for example A, B. Then you put arrow. Then if it's some small letter algebra like this, then you put that with. Is it okay?
What about the first question?
When these two. This one, right? You can always use this if you're worried. When talking about vectors, you can always use the second one.
Oh,
okay. Yeah.
And when is the wave above or below?
You can put either below or above. I think it doesn't really matter. You can put below here also.
Okay, thanks.
We are not very particular about it. Yeah. Any other questions?
Is it particular for a single or dual?
Sorry?
Is it particular for the first question? Is it very important?
For what?
Like 1 or 2.
1 or 2? You mean this one or this one?
Is it very important? Will I use 1 because of this?
You can always use 2 if you're worried. Let's use 2.
Okay, thanks.
Yeah. Any other questions before I move on? Okay, doesn't like it. So, question 2. Okay, so question 2 here, we have proved that if z minus 6i, the modulus z minus 6i is equal to z plus the modulus of z plus 2i, then the imaginary value of z is equals to 2. Okay, so here we call that z is an imaginary number. So z equals x plus yi. Okay, so you can go and substitute in. So that x plus yi minus 6i is equals to x plus yi plus 2i. Go ahead and group up the terms. X plus y minus 6 is equals to x plus y plus 2. Okay, so hopefully you all remember what is the modulus. What the modulus does is it calculates the distance or the magnitude of your complex number. So the modulus, if you square it, so the modulus actually is this one. X squared plus is equals to square root of x squared plus y plus 2 squared. Okay, so you can go ahead and square both sides. Okay, you square both sides, you get this x plus y minus 6 squared is equals to x squared plus y plus 2 squared. Okay, there's a square here. Then you can cancel out the x squared. So you just get y minus 6 squared equals to y plus 2 squared. So here you can just go ahead and expand this. Now, if you want, you can square root both sides and solve for it. But I'm not going to do that because you will need to think more. Okay, so you get this. Y squared minus 12y plus 36 is equals to y squared plus 4y plus 4. Now you just need to make y the subject and solve for y. Y squared and y squared will cancel. So here you will get 32 is equals to 16y. So your y is equal to 2. Okay, and y is the imaginary value of z, right? So y is the imaginary of z. So imaginary value of z is 2. Okay, so that's for question 2, part 1. Okay, part 2. treat the region consisting of all complex numbers satisfying this expression here, but instead of equal, there's a less than or equal sign. Okay, so there are two ways you can do this. Either you can do it geometrically, meaning you try to understand what does this mean, or you can just solve for it, like what I did in part A. So I'll do the second method first. So again, we are just solving for it. So I'm just copying down my working here, down here. So instead of the equal sign, we will have the less than or equal sign, right? So the less than or equal sign. So I'm going to replace all the equal sign by less than or equal sign. So I will write up to here. Okay, so you have 32 is less than or equals to 16y. And here I have y is more than or equals to 2. Okay, which means the region is when everything above the y equals to 2 line. So everything above here is everything here. Okay. Alternatively, even to identify, even to look at this geometrically, this means that the distance between z and 6i. So you want to find the region where the distance between your complex number and 6i is lesser than the distance between z and minus 2i. Okay, so this is, so you can look at geometrically. So you look at geometrically is y 6i is here. Okay, this is 6i. So minus 2i is here, minus 2i. Okay, so at what point is your points closer to 6i than 2i? So you can see that everywhere here is closer to 6i, everywhere here is closer to 2i. So in between here is fine. So it will be here. Geometrically, you can look at it like this, but I think most students will just solve for it as a inequality. Okay, so yeah. And now we got one more question for complex numbers here. So for this, suppose that z equals to 1 plus I, w equals to half plus square root 3 over 2i. Express z and w in polar form first. Okay, so first thing we do, let's go and express this in polar form. So z is equals to 1 plus I, w equals to half plus square root 3 over 2i. Why is it, okay, I've got a question here. Why is it 6i and minus 2i and not minus 6i and 2i? Because the distance between, the formula for distance is g minus something, is x minus something, to find the distance between x and that thing. So we have z minus 6i. So we have finding the distance between z and 6i. So we have z plus 2i. We are actually finding the distance between z minus 2i. So it's z and negative 2i. Okay. So you're finding the distance between z and negative 2i and z and 6i. Okay, let me move on. Okay, yeah. Okay, so here what I want to do is express this in polar form. So first notice that all this is in the first quadrant. Okay, both of this first quadrant, because all of these are positive. Okay, so because all these are positive, this will be in the first quadrant, so it will be somewhere here. Okay, so we want to express this in polar form first. So let's go and find the modulus for z. So the modulus for z is square root of 1 square plus 1 square, which is square root 2. And then the modulus for w will be square root of half square plus square root 3 over 2 square. Here you should get, I believe it's, okay, let's go and calculate this. This should be 1. This is 1 over 4 plus 3 over 4, which is 4 over 4, which is square root 1. So this is 1. Okay, so now we have the modulus for z and w. All we need to do is to find the argument. Okay, so find the argument for z. Okay, find argument of z, which is theta tangent inverse, okay, of y over x. Okay, so it is 1 over 1. Here you get 45 degrees, which is pi over 4. Okay, then the argument for w would be tangent inverse of square root 3 over 2 over half. Okay, so here you will get, I think 60 degrees, which is pi over 3. Okay, so you should always leave answer in radians. Okay, so now we can express this in terms of polar form. So z is equals to square root 2 cosine where is it? Pi over 4 plus I sine pi over 4. And w is equals to 1 times cosine pi over 3 plus I sine pi over 3. Okay, so the first part is done. We have shown this in polar form. Can we write CIS or need to write in full form? You can write CIS. That's fine. So if you want to write square root 2 CIS pi over 4, fine. Okay, so both are accepted. Okay, so from here, hence find the least positive integer n such that g star w to the power n is real. So first, what g star? So g star is basically z, but the argument, you flip the sign of the argument. Okay, so you have square root 2 cosine of negative pi over 4 plus I sine of negative pi over 4. Okay, then next, we want to take g star times w. Okay, we see what it is first. Okay, g star w, it will give me, because we are multiplying complex numbers. So remember that we are multiplying complex numbers. When you're multiplying complex numbers, you multiply the modulus. So square root 2 times 1 is square root 2. Then you add up the argument. So here will be cosine of pi over 3 minus pi over 4. Okay, plus I sine of pi over 3 minus pi over 4. So here you should get square root 2 cosine 1 over 3 minus 1 over 4. 1 over 12, right? Pi over 12 plus I sine of pi over 12. Okay, then we are going to raise this to the power n. And what is the condition here? We want the least positive integer n such that g star wn to the power n is real. So for g star w to the power n, so I'm basically going to take this whole thing here, I'm going to raise it to the power n, cosine pi over 12 plus I sine pi over 12, raise everything here to the power n. Here I will get square root 2 to the n cosine n pi over 12 plus I sine n pi over 12. Okay, so this is what happens if we raise it to the nth power. Okay, then from here, because I want this to be real, I want this function here to be real, which means that this has to be 0. Okay, the imaginary part has to be 0. So when it is sine n pi over 12, when it's sine 0, sine 0 is when you get sine pi equals 0, sine 2 pi also equal to 0, etc. You want this value to be an integer. So you will pick n is equals to 12. Okay, the least n, this positive n. So, I mean, you can take n equal to 0, but that is not positive. Positive is more than 0. Okay, so I have a couple of questions here. So, can we convert it to exponential form? Yes, you can convert to exponential form and solve. That's fine. Okay, can give an example of 3 chord. How to write the process? What do you mean 3 chord? Then I got one more is, do I need to write down my calculation when thinking process and thinking process when drawing diagrams? You should, but if you don't, you will still be awarded the full marks. Do we need to write Dimra's formula next to the line that I use it? If you want, you can. Otherwise, not very particular. Any other questions? Like -1 minus I in polar form. Okay, good. So you're saying -1 minus I in polar form. Okay, so here this time you're in the third quadrant. So we have -1 minus I is somewhere here. Okay. And for this, the argument will be slightly different. The modulus remains the same. So let's say z equals to -1 minus I. So the modulus of z is still square root 2. But for the argument of z, this time because we are in the third quadrant here. Oh, what the? I think I pressed something. Come. Okay. So because we are in the third quadrant here, right? Yeah, somewhere here, your argument will be this angle here. This will be your argument here. Okay, so to find this angle here, you will take. So just now we find the basic angle or the reference angle alpha is here. This is my alpha here. So this is pi over 4. Okay, so to get to this theta here, how to get this theta? Here you take negative pi, then plus. So your theta will be negative pi plus theta. So theta is plus pi over 4. G star is G conjugate. Yes, G star is G conjugate. G bar is also G conjugate. Okay, so your argument will be this. Do I need to write down which quadrant theta is in? No need. You just need to give me this value of theta. So you write negative pi plus pi over 4, I will know it's in the third quadrant already. You don't need to tell me it's in the third quadrant. Can I explain the last part again? How I determine n equals to 12? Can. Okay, because after I bring the power in from n inside, okay, by De Moivre's theorem, the power n will multiply to the argument here. So okay, n pi over 12, n pi over 12. Then because I want this expression here to be real, I want this to be real, this means that the imaginary part needs to be 0. Okay, which means sine of n pi over 12 has to be 0. Okay, and we cannot let n equal to 0 because it's not positive. So we want the smallest value of n, and the smallest value of n is 12. Because when n equals to 12, we have sine pi, and sine pi is equal to 0. Okay, when n equals to 12. So some various type of question they can ask is, for example, they can ask, for what values of n is this strictly purely imaginary? Also possible, but for that you will be solving for cosine n pi over 12 is equals to 0 instead. So just need to read the question and identify what they're asking. Okay. I thought it's cos the cos part n needs to be 12, so you get n. So you get 1 cos there for what's real. Okay, the cosine part does not matter. You need to ensure that the imaginary part is 0 for your complex number to be real. Because let's say I have some complex number here, let's say we have z equals to x plus yi. Even if my x is some real value here, let's say it's 2, but if my y is not 0, let's say it's 3, then this is still a complex number. It's not purely real. That's why we need to make sure the complex part, the imaginary part, completely vanishes, which is when it's equal to 0. Okay, so the cosine part does not matter, does not affect whether my complex number is real or imaginary. At least for this question here. If I want my value to be purely real, my imaginary part needs to be 0. If I want my complex number to be purely imaginary, then my real part needs to be 0. Any other questions? If on that, I'll wait for 1 minute, then I'll move on. This is the same questions. So let me move on. So next question. Okay, find the matrix A so that A minus 4i to the power of the inverse is equals to 1, 0, 1, 1. Okay, so I mean we've seen this quite a couple of times in tutorials already. So the first thing you do, you apply inverse on both sides of the equation. Okay, so apply inverse on both sides of the equation. A minus 4i inverse equals to 1, 0, 1, 1. So apply inverses. So inverse will cancel each other out. So we have 1, 0, 1, 1 inverse. Okay, so let's calculate this 2 by 2 inverse. So you need to know how to, you are required to know how to evaluate the inverse of a 2 by 2 matrix. So first, you find the determinant is A over the determinant AD over BC. Then you swap these two places. So for A inverse is equals to 1 over AD minus BC times, you swap these two, DA, negative B, negative C. Okay, I'm using this formula here. Okay, so this is 1, 1. Negative 0 is 0. Negative 1 is here. Okay, then AD minus BC. So let's replace this AD minus BC is 1 times 1 minus 0 times 1. Okay, A is 1, D is 1, B is 0, C is 1. And this, you also evaluate, you get 1. So all you get is 1, 0, negative 1, 1. Okay, A minus 4i is this. Okay, and here, all you need to do is move this 4i over. So that A is equals to 1, 0, negative 1, 1 plus 4i. I is your identity matrix. So it's 1, 0, 0, 1. Okay, you can multiply the 4 inside, put inside 4, 4. So all after you evaluate this, you should get 1 plus 4 is 5, 0 minus 1, 5. Okay, that's for matrix A. Okay, let me move on. Part B. So consider the matrix where X is a unknown real number. Show that B is invariable for all values of X. So for this question, what you're trying to show is that the determinant of B is never 0. Okay, so remember, invariable means your matrix is inverse and your determinant is not 0. So what I want to show is that the determinant is not 0 for all values of X. Okay, so let's go ahead and do this. So let's now calculate the determinant of B. Okay, we can do along any row or any column you like. So what row and column shall we take? Maybe we can do along the first row. Just since there's a 0 here. Okay, you can either do first row, second row, or the second column or third column. I think all these are good choices. So let's go ahead and take the first row. Okay, we are doing along the first row. So remember, you should put a plus, minus, plus here. Okay, so we are going to do cofactor expansion. So plus 1, put 1. Then the reduced matrix is this part here, 1, 0, x1. Okay, times the determinant of 1, 0, x1. Okay, minus 0 times the determinant. So determinant of x, 0, minus 1, 1. Okay, and then plus 2x squared of this part here, x1 minus 1x. Okay, let's go and evaluate this. So 1 times 1 is 1. 0 times x is 0. So 1. I don't need to evaluate this because this is 0 times whatever inside here. So this is first plus 0. Okay, it doesn't matter. Then here plus 2x squared times x is x squared minus 1 times minus 1. This is plus 1. Yeah, plus 1. Okay, and this will give me 2x squared plus 1, and plus 1. You want to expand it, you can. So we can expand out to get 2x to the power 4 plus 2x squared plus 1. Okay, notice that this part here, is always more than 0 because they are even powers. Okay, so x to the power 4 and x squared is always positive or more than 0, at least 0, and we are adding 1. So this thing will always be more than 0. Okay, will always be more than 0. Not just equal, it will always be more than 0. So since the determinant of B is always at least 1, you want to put at least 1, you can, at least 1, which is more than 0 for any x. Okay, your V is invertible for all values of x. Okay, for all x. Okay, that's for matrices. I'll wait for any questions if you guys have any. There doesn't seem like there's any questions. So let's move on. So can we say that B not equal to 0? Yes. Which is not 0. The group not 0. Can. Okay, last question. Any last minute questions? Doesn't seem like there's any. I want to move on. Okay, let's move on. Question 4. So here we are finding limits. So by the way, expect again, you should expect similar weightage in your paper. You probably have one question on matrices, one on vectors, one on complex numbers. Everything else will be on calculus. Okay, meaning your limits, differentiation, and integration. So if you haven't started studying, you should focus on them. Okay. Okay. So question 4 part A. So finding the limit here. So here, if you try and substitute, let's see what happens. So here you get 0 over 0, right? You get 0 over 0. Yeah, okay. But so you can apply L'Hopital's rule, but that doesn't feel very fun. So let's not apply L'Hopital's rule. Okay. Most of the questions you usually don't need to apply L'Hopital's rule. Okay. So if I don't want to apply L'Hopital's rule, let's see what we can do. What's the limit of x approaching 0? Okay, so I'm going to split the terms one by one. So you get e to the x times sine to the 2x times 1 over tangent 3x. 1 over tangent 3x we can rewrite as cosine 3x over sine 3x. Okay. Then we can group up the cosine 3x and the e to the x, cosine 3x. Okay, these two terms don't cause an issue, but now we have sine 2x times 1 over sine 3x. Okay, so we are going to use one identity that we went through in the tutorial and in the lecture. That is our sine x over x as your x. This is 1. So we want to use this somehow. So what we're going to do, you notice that there's a 2x here. Okay, there's a 2x here. So if we divide by 2x, then we can use this property, right? Okay, when we divide by 2x, then we use this property. So we cannot just randomly introduce the 2x however we want. So when we divide by 2x, we have to multiply by 2x. Okay, and then similarly, because I want to introduce 3x here, so I want to put a 3x here, I will also need to introduce 1 over 3x, okay, to make it 1. Okay, so let's just go ahead and evaluate the limit. So this two part, this is e to the power 0, which is 1. Cosine 0 is 1, so it is 1. This part here is 1. This part here becomes 1. And here, you have 2x over 3x. So here we can rewrite as 2x over 3x, which is 2 over 3. So this is times 2 over 3. So final answer is 2 over 3. Okay, 1 times 1 times 1 times 2 over 3. So you get 2 over 3. Okay? So here you can also apply L'Hopital's rule if you want. So alternate working for this, let me apply L'Hopital's rule. So L'Hopital. Okay, if you want to apply L'Hopital's rule, you can. You just need to be careful when you are differentiating. So here, e to the x sine 2x over tangent 3x. So here, do we need to prove sine x over x by L'Hopital rule? You do not prove sine x over x equal to 1 by L'Hopital rule, by the way. That is the proof. I don't know whether you went through in lecture or not, but you cannot use L'Hopital rule to prove it. You just use the fact. You can just use this fact. You don't need to prove anything. Just use this. So this should be a fact that you should know.
So I don't need to prove that.
You do not need to prove this. And if you want to prove this, it's not by L'Hopital rule.
Oh, why? Because sine x is 2, 0 and x is 2, 0. So
yes, but that will be a circular proof. So how come you can use L'Hopital rule on this? Is the question we will ask. So usually we do not apply L'Hopital rule for sine x over x because we use this to prove L'Hopital rule. So you cannot use L'Hopital rule to prove this. It's circular logic.
Oh, okay.
Yes, but anyway, you only need to know this property here. You do not need to prove it.
Okay, thanks.
Okay? You just need to use this.
1 minus cosine.
Yes, you can just use it. You don't need to prove it.
Okay.
Yeah, okay. So let me come back here. So here, even though apply L'Hopital rule, you can. Okay, so first, before applying L'Hopital rule, please check. You have 0 over 0 or infinity over infinity. And you need to write out. Okay, here we have 0 over 0. Wait, where have we 0 over 0? So I substitute x equals 0, I have sine 0, which is 0. Tangent 0 is also 0. So I have 0 over 0. So we can apply L'Hopital rule. Okay, so by L'Hopital rule. So you can go ahead and differentiate the numerator and the denominator. So differentiating the numerator, you have e to the x times 2 cosine 2x. Okay, plus e to the x sine 2x over secant square 3x times 3 to the limit of x approaching 0. And now we can go ahead and apply the limit. Here, this thing will become 0. This thing will become 0 here. And just to be more clean, here you have 0, they have 1 times 2 times 1 over 3 times 1, which is 2 over 3. So yeah, so you apply the limit. Okay, so let me come back to part B. Okay, so for part B, we have the limit for square root x squared plus 1 plus x over sine x plus 2. Here, the biggest hint is you have x approaching infinity and sine x. The moment you have this, you should think of squeeze theorem. There is almost no other way for you to solve this other than by using squeeze theorem. So most other methods here will be wrong. In fact, I think all other methods here will be wrong. So that's a tip for you. If you see the limit of x approaching 0 or sine 1 over x or cosine 1 over x, you can use squeeze theorem. Okay, another one is limit of x approaching infinity or negative infinity of sine x or cosine x. You also use squeeze. So here I see limit of x approaching negative infinity and sine x. Okay, so my mind will start to think, okay, I should use squeeze theorem for this question. Okay, so we will be able to squeeze this later on. That's my intuition. So the squeeze should look like this. So this is x squared plus 1 plus x over sine x. This will be between square root x squared plus 1 plus x over negative 1 plus 2 square root x squared plus 1 plus x over 1 plus 2. Okay, so all we need to do is check whether this limit is equal to this limit. And if they are equal, we can conclude by squeeze theorem the limit will be that value. Okay, but if we somehow find that they're not equal, then you cannot conclude anything. Okay, so anyway, all I need to do is check the limit of this now. Okay, so the limit, so let the limit of square root x squared plus 1 plus x approaches negative infinity. Okay, for this, if you go and substitute, you won't get anywhere. You have square root infinity minus infinity. again, this is a indeterminate form. So you cannot just substitute and you get infinity minus infinity and you write equals 0 like this. This is incorrect. Okay, this is incorrect. So we cannot just substitute because we don't know which infinity is bigger or smaller. Okay, so here we have a square root. So your thought process should be to rationalize this. When you see any square root, I would say 90% of the time, you will rationalize. Okay, so we have this function here. Let me write out bigger. X squared plus 1 plus x. We are going to rationalize this by multiplying by the conjugate. Square x squared plus 1 minus x. Square x squared plus 1 minus x. Okay, so you can go ahead and simplify this. Here you will get x squared plus 1 minus x squared. Okay, over whatever is here. X squared plus 1 minus x. Put a limit here. Negative infinity. And here, x squared minus x squared is 0, so we can have the limit of x approaching negative infinity of 1 over whatever is here. Okay. And here, notice that if you go and substitute the limit in, this time we will get a more definite answer. Here, notice that if I substitute infinity inside this square root, I have negative infinity squared, which is positive infinity. Okay, then the square root of positive infinity is positive infinity. So this is positive infinity. Negative x, as x approaches negative infinity, this whole thing will make it into a positive infinity. So now in the end, I will get 1 over positive infinity, which is 0. Okay, and because this limit here is 0, this limit here is 0 by squeeze. So this limit here is 0 and more space. So let me have a page. So because this limit here is 0, so remember that my original squeeze, I wanted to squeeze this between sine x plus 2 of this plus x over 1 and square root x squared plus 1 plus x over 3. This and this, they are both 0. So we have 0 and 0 here. So by squeeze theorem, you can say that the limit of the middle function here, okay, it must be of negative infinity, it must be 0. Okay, by squeeze theorem. Okay, so that should be this question here. So let me look at the questions in chat. I rationalize why I can do squeeze theorem. Is that okay? Yes, that's okay. For limits, is there a specific way to know how to deal with it? Because there are many ways like common factors, rationalize, divide by half power, sin over x rule, L'Hopital rule, and squeeze theorem. Okay, so like I said, for squeeze theorem, mainly is these two. Okay, I would say in this course, mainly you will see, when you see these two happening, you use squeeze theorem. Okay, for common factors, you should try and use it first. If you have a fraction and there's a common factor, you can go and divide it first. There's nothing wrong with doing that. Okay, rationalize only applies for square root. Okay, and then divide by half power is when you are dealing with infinite powers. Sin x over x rule, this one you apply it when you see sin x over x. If you have some trigonometry, you apply sin x over x. L'Hopital rule, you have an indeterminate form. 0 over 0 or infinity over infinity. Do I need to know how the limit equal to 0, like write the infinite sign down or just write 0? You mean here, right? Here, if you just write equal to 0, it's fine. If you know why is 0, it's fine. You don't need to put an arrow here. But if you write down the arrow, I think it will help yourself also lah, to see better. How did I get the denominator for left hand side and right hand side? Oh, because sin x is between -1 and 1. Right, sin x between -1 and 1. So how come -1 is on the right? Because when I make my denominator smaller, my value gets bigger. Right? My value gets bigger. So same thing for the left. If I make my denominator bigger, my value gets smaller. Okay. Yeah. Any other questions before I move on? Hey, can I show the L'Hopital rule method again? Can. Where is it? Here. This is good. I'll be sending these annotated notes on the Telegram anyway. So, yeah. Okay, any other questions?
May I ask, like, the L'Hopital's rule, if I got something like gx fx and the power is gx and the limit of fx and gx are all 0, then no, the fx limit is infinity, but the gx is 0, then can I just like use L'Hopital rule, like turn it into fx derivative and the power of gx derivative?
No, you cannot apply directly like this. You're saying you have a function limit of x approaching 0 or some value of fx to the power of gx, is it? To the power of gx.
Yeah.
This, right? And then you're saying that if this approaches infinity and this approaches 0.
Oh, yeah. Can I like, is the same as fx derivative and to the power of gx derivative?
No, you cannot apply L'Hopital rule like this. L'Hopital rule only apply when it's a fraction, fx over gx.
Oh,
if it's not a fraction, you cannot apply L'Hopital rule.
Okay.
So if you have this, if this happens, what you have to do is you can apply the e to the ln trick here. So here, instead of fx, you have fx to the power of gx. Here you can make this equals to e to the power of ln or fx to the power of gx. And this is equals to e to the power of ln fx times gx here. And then you can convert this to a fraction and you can apply L'Hopital rule that way. And then you check if this, then you check what's the power of this. And if this power is, let's say 0, you have e to the power of 0, which is 1. If it's some other value, then you can check yourself.
Okay, thanks.
Okay? Yeah.
Thanks.
Any other questions? Okay, doesn't look like there's any. Let me move on. Okay, question 5. We're halfway there already. We're only halfway there. Okay, so we have the function here, such that this is differentiable. Okay, this type of question appeared in your midterm already. So I hope everyone knows how to do this. Okay, so for this function to be differentiable, it means that my function here must be continuous. So you can go and check the continuity by checking the limit. Okay, the left and right limit has to be equal. So the limit of x approaching 4 from the left of fx is equals to the limit of x approaching 4 from the right of fx. Okay, you can check the limit. You can also check it's equals to f of 4. Okay, it doesn't really matter what you check. As long as you check this, either one is fine. Okay, so let's go and equate them together. So here you have the limit. You have the limit of x approaching 4 from the left. From the left, we have square root x. So put square root x here. Okay, from the right, we have the limit of x approaching 4 from the right, ax plus b. So my x approaches 4. So I have, this is square root of 4, which is 2, is equals to 4a plus b. So 4a plus b is equals to 2. So we have two unknowns in one equation. So we cannot really get anywhere. So the next step, okay, the next step here is you just check the left and right derivative. Okay, because I want my function to be differentiable, I assume it is differentiable. So for f to be differentiable, okay, you can differentiate the left and the right side, and they have to be equal. So the left derivative has to be equals to the right derivative at all points. So particularly at 4, okay, the left derivative is you differentiate square root x, you get 1 over 2 square root x. And this is equals to ax plus b. Ax plus b, differentiate this, you get a. Okay, and at the point 4, at the point at x equals to 4, you have this. Okay, so all you need to do is calculate what is a. So a is 1 over 2 square root 4, which is 1 over 4. And then b, just substitute this inside this. So you should get b is equals to 1. B equals to 1. Okay, I think this shouldn't be too difficult as well. Take 1 over 4 and 1. Any questions?
Do I need to like use the a and b value to prove that it is really the differentiable?
No need. I mean, no need. Yeah, you can if you want, but there's no need to. Okay, there's no question. Let me move on. Question 6. Find the global maximum and global minimum of my function square root t times 4 minus c on this interval here. Okay, so first thing you know, there's a closed interval here. Closed interval. Okay, then you see maximum, minimum. So you should be thinking of the closed interval method. Okay, my function here is continuous. Okay, because my function is continuous and I'm on a closed interval here, I can apply the closed interval method. Okay, so let's go ahead and find the derivative. So f of t, I'm just going to multiply this square root t inside, so we get 4 square root t minus t to the power of 3 over 2. So f prime t, just differentiate this. You should get 2 over square root t, then minus 3 over 2 square root t. Okay, then can we factorize this? Yes, we can. So here you can factorize this by what you do is this is square root t at the top, right? The square root t here. So multiply square root t here. Okay, or if you want, you can do the other way around. Do it for the other one. It doesn't really matter. So multiply by square root t. So here you can, after this, you can factorize that. After that, you can factorize to get, let me see, this is 2 over square root t minus away 3t over 2 square root t. Okay, so we can take out 1 over square root t. Okay, then we get 2 minus 3 over 2t. Okay, so can get something like this. And remember that we're going to find our critical points. Can we combine the fractions? Here you can combine the fractions also if you want. Up to you. Okay, the goal is you want to find critical point. Okay, as long as you can solve for the critical points, you're fine. Okay, so first, my derivative is this. Okay, my derivative is this. So critical points, remember your critical points include your stationary point and your singular points. Okay, so you have your stationary points and your singular points. So stationary points is when your f prime x is equal to 0. You solve for this equal to 0. It's basically this part is equal to 0. Okay, 2 minus 3 over 2t is equal to 0. So this is when t is equals to 4 over 3. 4 over 3. Okay? Then the second one is when your f prime x, okay, not defined. Your f prime x is not defined. Look at this fraction here. It's because it's a fraction. So it's not defined when your denominator is equals to 0, right? So your stationary point is when t equals to, your singular point is when t equals 0. Okay, so we got 2 points here. We collected 2 points. Let's go and substitute all the points inside. Okay, all my values. So calculate f of 0, f of 4/3. Okay, then we got the end points here, 0 and 4. Okay, so this is the end 0, this is the end point already. So it's fine. So we got f of 4. Okay, calculate all these 3 points and check what is the biggest and smallest value. So f of 0 is equals to 0. F of 0 equals to 0. F of 4/3. Let me press my calculator. I will get 16 square root 3 over 9. Okay, then f of 4, also 0. Okay, then here the global max is 16 square root 3 over 9. The mean is equal to 0. Okay, so that's for this question here. Can I explain the singular point part? Yes. So for the singular point is when, singular point is when your derivative does not exist. Meaning, because my derivative is this, right? This is my derivative, 1 over square root t times 2 minus 3 over 2t. Okay, this does not exist when your denominator is 0, right? This is actually a fraction, right? This you can rewrite 2 over 3 over 2t over square root t. I mean, the numerator is just a polynomial, so it will always be defined. But the denominator, it has an issue here. The issue is that for this, because this is a fraction, my function here cannot divide by 0. So this cannot be 0. So square root t equal to 0 is my critical point. To solve for this, you get t equals 0. And okay. Must leave global max as fraction. No need. They never write anything. But you should write as accurate as possible. Okay? You have to write it as accurate as possible. I mean, you can use the 3SF, but usually try and leave your answer as exact value. For question 5, can we just use question 5? F prime x to solve. Cannot. For question 5, if you only use f prime x, meaning you only check the derivative, you will only solve for a one. You cannot find b. Right? You will not be able to solve for b. So it's not possible for you to only use the derivative to solve it. Because when you differentiate ax plus b, your b disappears. Then you cannot find b already. It's gone. Okay. Then last question. A little off topic, but to differentiate a global max from a local max, all I need to see if it's bounded. So if it's bounded, global max. If not, local max. No. Wait, let me think. This method here will give you the global maximum. Local maximum, you will get it by doing the first or second derivative test. That is all. You will not get local maximum by doing the closed interval method. You will get the global maximum. Any other questions? So what happens if it's an open interval, just 0 and 4 not included then you cannot use this method because closed interval method only applies for closed intervals. You have an open interval, you cannot apply the closed interval method. Okay? Then one method to apply. Then you cannot find a global max or global mean. You will be finding local max and local mean. Okay? Yeah, you need to read the question. Because of extreme value theorem, remember that extreme value theorem says that only in a closed interval you are guaranteed a global max and global mean. You cannot find a global max or global mean in a, or you cannot find both in a open interval. You maybe can find one depending on the function, but you cannot find both. Okay, so let me move on if there's no other questions. Okay, question 7. Okay, so show that it has exactly one root. Okay, whenever we have this type of question, right, they say show it has exactly one root. You will be combining IVT plus MVT, or both, up to you. Okay, when you say exactly one, it is most of the time using IVT or MVT. Okay, so let's first, we want to show it has exactly one root first. So usually there's only one question about proving. So is there any proof question here? Just check. So don't have. Yeah, this will be the proving question for this. If the value of t where f prime t is 0 is outside 0 and 4, then you don't care about the point. So if the value of t where f prime t is 0 is outside 0, 4, you're saying when you solve f prime t, right, you get the point outside 0, 4, then you do not need to, you just use your endpoints, f0 and f4. Okay, you just use the endpoints. Yep. Okay, so can use first or second test. If you want to find global max, global mean, you can, but you need to do some certification. Generally, global max and global mean, you will just use closed interval method. If you want to use first and second test, you can. I'm not stopping you. But you will miss out. You will miss out on the endpoint. Because the endpoints may not necessarily be a stationary point. And if you use your first and second derivative test, you will only be checking for the critical points. Okay, let me move on. So my function here, first, use IVT. Okay, use IVT. So look at the function here, my fx is equals to x cubed plus x minus 1. Okay, so clearly f is continuous. Okay, again, before applying any of the theorems, you should always write any conditions that needs to be applied. Okay, so for when you're applying the intermediate value theorem, you need to make sure my function f is continuous. Okay, this is just a polynomial. This is continuous. Okay, then what we have to do, we have to find one point where it's positive, one point where it's negative. So let's take any point. So f of 0, what's f of 0? Negative 1. Okay, f of 1, 1. Okay, since f is continuous on 0, 1, on the closed interval 0, 1, okay, by IVT, there is a root. Okay, there is a root such that f of c is equal to 0. Okay, there's a root such that where c is between 0 and 1. So now I show that my function f has at least one root. Okay, it has at least one root. Does it have more? I don't know. I know it has one. Maybe it can have 2, maybe it can have 3. But I'm guaranteed at least 1. Okay, so now we want to use MVT. Okay, MVT to show there is at most one root. Okay, there's at most one root. So for MVT, what you are typically going to do is you will suppose it has more than one root. Okay, let's suppose f has more than one root. Okay, so 2 roots or 3 roots, I don't know, more than 1. Okay, so meaning that I have f of a is equal to 0 and f of b equal to 0. Because a and b are my roots, right? A and b are my roots. Okay, and a not equal to b. Okay, now here we will be applying the mean value theorem. Okay, by MVT, by mean value theorem. Okay, there is, okay, we don't use this. There is a C between A and B such that f prime C, okay, is equals to f of B minus f of A over B minus A. And because we know that f of A and f of B, they're both roots. They're roots of my equation here. Okay, they're both roots, which means that f of B equals 0, f of A also equals 0. So that's 0 minus 0. I don't care what is B and A. I know that they're not equal. So we have f prime C is equals to 0. Okay, so look at the flow. We have, so if we have two roots, if two roots exist, then somewhere between the two roots, the derivative must be 0. Okay, but now let's see where this problem occurs. Okay, so however, your function fx is equals to x cubed plus x cubed plus x minus 1. If you take the derivative, it's 3x squared plus 1. 3x squared plus 1, it will never be 0, right? 3x squared is always more than 0. So this is always more equals to 1, which is never 0. Okay, this is impossible, right? So this is impossible. Impossible for my derivative to be 0, which means it's impossible for me to have two roots. So there is at most one root. Okay, so let's look at the argument again. If we have two roots, then f of A, f of B is equal to 0 for some A and B. Okay, and by mean value theorem, okay, we know that f prime C between A and B is equal to this formula here, f of B minus f of A over B minus A. And because I know f of B and f of A are both 0, 0 minus 0 is 0. So if we have two roots, the derivative must be 0 somewhere. But my derivative, after I differentiate my function, I have 3x squared plus 1. This is always more than 0, which means it's impossible for me to have two roots, okay, two or more roots. So there can only be at most 1. Okay, you combine IVT and MVT, you will get exactly 1. Okay, so IVT plus MVT, you have exactly 1 root. Exactly 1 root. Okay, so that's for the proving part here. So the proving part, if you can. Okay, so must I say f is continuous on AB and differentiable on AB? Yes, you need to always state it. I mean, I didn't state it, but you should state it. So here, you can write here, because f is continuous and differentiable. Okay, continuous on AB, differentiable on open interval. Okay, so a graphical method, a graphical way for you to look at this is if you have two roots, right? Let's say here and here. Then let's say my function go up. It must come down somewhere. Okay, let's say my function is coming out, right? Eventually it must come down. And at the turning point, the derivative is 0. That's what it means to have derivative to be 0, right? So basically, right, if you have two roots, when the function, let's say, is going up, okay, if it's going up, it must come down. But my function here, what we show here is that my function here, the derivative is always more than 0. So it's always increasing. It cannot come down. Okay, it's impossible for it to come down like this. Because at this point, your derivative is equal to 0. That's why it's impossible for you to have two roots. can explain again why FA and FB equals 0. Because I suppose that FA and FB, they are roots of my equation, which means FA and FB, FA equals 0 and FB equals 0. And from that argument, we can see that it's impossible for that to happen because the derivative is always positive, always more than 0. Okay, any other questions?
So when explaining it, we have to use the mean value theorem instead of just showing like the first derivative, right?
Yes, you have to use the mean value theorem.
Oh, okay, thanks.
Okay, so let's move on to the second part. Second part, just using Newton's method. This one, not much to it. So here, did they say any x0? Never. Okay, they didn't give me any x0, so I will just use x0 equals to 1. Because we have f of 1 is equal to 1, f of 0 is also minus 1. Okay, up to you to use negative 1 or 1. Okay, so convert it to two decimal place. So x0 equals 1, x1 is equal to x0 minus, minus f of x0 over the derivative f prime x0. We can pick randomly. Yeah, you can pick somewhere close, somewhere that makes sense. Don't pick 100 lah. Don't pick x0 equal 100 or something. Because you already use IVT to show. You already use IVT to show that a root exists between 0 and 1. Okay, so we already use IVT to show it's between 0 and 1. It doesn't make sense for you to use a point further than these 2 points. So 0 is negative 1, here is 1. So somewhere in between you cut. Okay, so you should ideally use somewhere near this. So you can start from 0 or 1. Okay, I'll use 1. If you want, you can use 0. Any other points, I think you can, but you will take more steps. Okay, remember we are trying to correct this to two decimal place. So you won't stop until your value stabilize. And if you start very far away, you will take a very long time to come to this point. Okay, so let's say start from x0 equal 100. You will take more iterations to come to this point. Okay, your end product will be the same answer, but you will take more steps. Okay, anyway, let's continue here. So here, x0 is 1. Okay, minus f of x0 is 1 over the derivative 3x squared, 3 of 1 squared plus 1. This is 3 over 4. Okay, so x1 is 3 over 4. So x2 is 3 over 4. x1 minus f of x1 over f prime x1. Okay, so this is 3 over 4. Minus 3 over 4 square plus 3 over 4 minus 1 over 3 times 3 over 4 square plus 1. Use my calculator to see what I get. 3 over 4. But it is cube, sorry. .686. 0.465. You want up to two decimal place. So previously it was 0.75. So you can see you haven't stabilized yet. So we will just keep doing. So x of 3 is x2 minus f of x2 over f prime x2. So use this value, plug in here. Just keep repeating until you see that eventually, right, you will get 0.68 something. Then you see that, oh, the two decimal place is stabilized already. Then you can stop. Okay. The final answer should be 0.68. Okay, you will need to do one more time to ensure that it's stabilized.
Oh, but I got a question like 0.686, it will be like 0.69.
Correct.
So do I need to get another iteration?
Yes, you cannot stop here. You cannot stop here. You need to repeat this until it's stabilized.
Oh,
so if you take this, right, this is rounded out to be 0.69, right? So if the next iteration gets 0.68, you have to repeat one more time to get 0.68, and then you can stop.
Okay. Thanks.
Okay. Any other questions? No? Okay. So anyway, this one you're just applying the Newton's method. Just a reminder, the formula is given down here. It is given here. This one. Okay. Let me move on. Question 8. Okay, we're almost done. Okay. Question 8 is here. Okay. Using the definition of derivative, okay, find f prime x. Okay, I think this is the tutorial question. Okay, this is the tutorial question. So remember that fx is equals to x square x. This is equals to x squared if x more than 0, negative x squared if x less than 0. Okay, so you need to show for both cases. Find both cases. So for x more than 0, for x more than 0, f from x. But the definition is the limit, okay, of y minus x, y approaching x, of fy minus fx over y minus x. You just need to plug in accordingly. Y absolute of y minus x absolute of x over y minus x. Okay, and because x is more than 0 and y is also more than 0, here we have y squared minus x squared over y minus x. Y approaching x. And here you can divide to get the limit of y approaching x to be y plus x to get 2x. Okay, if x is more than 0. If x less than 0, same thing here, f from x is equals to limit of y approaching x, y as over y minus x as over x over y minus x. But this time, because x is less than 0, x is less than 0, so y also, when y approaching x, y is also less than 0. Okay, so here, here you should get negative y squared plus x squared over y minus x. Same thing here, you can divide. You should get negative the limit y approaching x. Okay, negative of y plus x. Here you get negative 2x. Okay, so negative 2x. Then finally, for x equals 0. Okay, go ahead and find the limit. So this time we have y approaching 0, so f prime 0. Okay, so y approaching 0. No need to put x already because I know it's 0. So of y absolute of y minus 0 absolute of 0 over y minus 0. Okay, then here you should get the limit of y approaching 0, absolute of y, which is 0. So here, f prime x is equals to 3 different values. 2x, negative 2x, and 0. If x more than 0, x equals 0, x less than 0. So you can actually combine them to be 2 of x minus x if x more than 0, if x less than 0, and this can be written as this. Okay, I mean, this is just a tutorial question, I think. So it shouldn't be too difficult. Why can't I directly use the x plus h formula instead? You can. Nobody said you can't. It's the same formula. Do I need to show y less than 0? No need. You already show here. You already show that x less than 0 here. I show it because maybe you all don't know why. Okay, so I think there's not much to discuss here. You're just applying the definition. Okay. If there's no questions, let me move on. Is
it necessary that we have to solve for both x is less than 0 and greater than 0?
Yes.
Can't we solve one and say that similarly following other?
No, that is not allowed.
Okay.
Yep. Because this is a piecewise defined function. So for piecewise defined function, you cannot just say, oh, similarly, something. If y less than 0 and as x less than 0, isn't the denominator minus y plus x? No, the denominator is still y minus x. I mean, it only affects the sign of the value itself. It doesn't affect the expression. The reason why this one became negative y squared is because this is equal to negative y. That's why it changed. Okay, this one remains the same. Okay. Any other questions? No? Okay. Question 9. Question 8. B. Okay. So here, using implicit differentiation, solve for this. So how will we do this? So here you will let y equals to cosine inverse x. Then you're just going to take cosine on both sides. Cosine y is equal to x. Then cosine y. Then differentiating respect to x. Okay, differentiate cosine y. So this one, be careful. So differentiating cosine y, you will get negative sine y, okay, times the derivative of y, which is dy over dx. Okay, and this is equals to 1. So dy over dx is equals to 1 over negative sine y, so negative sine y, given like this. Okay, and then we're going to use some identities here. Sine square y plus cosine square y equals to 1. So sine y will be sine square y equals to 1 minus cosine square y. And sine y will be the square root 1 minus cosine square y. Okay, so here we have negative 1 over the square root of 1 minus cosine square y. Okay, cosine square y is written like this, cosine y squared. And here we have negative 1 over square root of, because y is cosine inverse x. So we have 1 minus cosine of cosine inverse x squared. So this part here will cancel out. We get negative 1 over square root of 1 minus x squared. Okay, 1 minus square root of x squared. Okay, so okay, so that's for this question here. That's all I need to do, right? Show that this is this. Yeah. So dy dx is equal to this. Dy dx is the same as saying d of dx of cosine inverse x. Okay, this is dy dx. Okay, so this is also not too bad. Just applying implicit differentiation. Okay, any questions? I see one question. Why not x less than 0 and x more than or equal to 0? I assume in the previous question. This one here. I'm not sure what you mean. So this one here you get 2 times x if x more than or equal to 0, negative x if x less than 0.
I mean, like, Professor, you discuss like, you take x, specifically x equals 0. Can I put like x equals to 0 and x over 0 together? Like, only categorize like 2?
I'm still not sure what you mean. This is 2, right?
No, like the top, like discussing when
This?
in the top we discuss like three times. So can I like put the discussion like x equals to 0 and x over 0 together?
No. You have to split them into different cases because the derivative may behave differently at a point at a piecewise at the endpoint of piecewise defined function. So this is the endpoint, right? So you need to check the endpoint carefully. That's why we have to check x equals 0 separately.
Oh, okay.
Okay.
Oh, thanks.
Okay. So I can explain the last 3 steps for B. Can. Okay. The last 3 steps. Okay, so maybe we erase everything here. Then explain again. Okay. So first, dy dx. We start from here. Okay, dy dx is equal to negative 1 over sine y. Okay. So dy dx is equal to negative 1 over sine y. So sine y is given here. Okay, I'm just going to do a substitution. So negative 1 over square root of 1 minus cosine square y. Okay, cosine square y. So cosine square y is the same as writing cosine y squared. Okay, cosine y squared. Okay, then here we will substitute y. Remember that originally y is cosine inverse x. So y is equals to cosine inverse x. So here, 1 minus cosine of cosine inverse x. Okay, so I'm going to square everything here. Okay, and here, notice that here, this cosine and cosine inverse, they are reverse processes of each other, so they will cancel out. So 1 minus x squared. So this one, you can just remove the bracket, right, x squared.
So for the cos y, can I just substitute x straight away? Because you already proved cos y equals x.
You mean here?
Yeah.
You want to write this as, yeah, you can just substitute here. Just because y is, yeah, you can just do a substitute here to be x. That's fine.
Oh, okay. I think
Can we equate cosine y squared equals to x squared? Yes, you can equate cosine y squared to x squared. In the end, you should simplify to x squared. Okay? Okay, if there's another question, let me move on. Question 9. Okay, I think we're almost done. 4 more questions. Okay, we got 1 more question here. Do I need to show y is in 0 to pi? Y is in 0 to pi so that sine y isn't negative. I'm not sure what you mean. Sine y isn't negative.
Like when converting sine y by 1 minus like sine y equals square root 1 minus cosine to the power of 2.
Yes.
But that one, so they didn't choose the negative one because sine y is like 0 to pi. So the
Okay, I see what you mean. Yes. You will take y to be inside. You will take y to be inside 0 to pi.
okay. Thanks.
Will this meeting recording link be sent? I don't think. Oh, I'm recording. I don't think I'll be sending this though. A bit troublesome for me to upload this. Yeah, you can record it for yourself if you want, but I won't be uploading anything. It's a bit troublesome for me. It's like over 2 hours long, or 1 hour plus. Okay, let me move on. Question 9. So fx is equals to the derivative, the integral of 1 to x t ln t dt for x less more than 1. Okay, here, straight away, you should know you are gonna differentiate this you want to find the second derivative. Okay, so what we are going to do is we're going to apply the fundamental theorem of calculus. So by FTC, okay, f prime x, okay, is equals to d over dx integral 1 to x t to the power ln t dt. So by the fundamental theorem of calculus, here you will immediately get x ln x. So f prime x is x ln x. So we want to find the second derivative. Okay, we want to differentiate this one more time. Okay, here you will need to do some implicit differentiation again. So that y is equals to f prime x. So y equals x ln x. So we are going to ln both sides. So we have ln y is equals to ln x to the power of ln x. So ln of x to the power of ln x. And this is ln x times ln x. Okay, this is ln y equals to ln x squared. Okay, then we can just go ahead and differentiate this respect to x. So ln y differentiate respect to x, you have 1 over y, then differentiating the inside because of chain rule, that's 1 over times dy dx. Okay, then differentiate ln x squared is 2 ln x. 2 minus 1 is 1. Then times the derivative of ln x is 1 over x. So here you can just, so this is equals to this. So here we have dy dx is equals to y times whatever is here. So y times 2 over x ln x times y. Okay, and because I say that y is x ln x, all you need to do is just substitute x ln x. Okay, just substitute x ln x. So here is x ln x. Then you can just solve here. No need to simplify. Okay, no need to simplify. So let me just check. Then all you need to do, so because dy, y is f prime x, so dy dx is f double prime x. This is f double prime x. Okay, this is dy dx, which is equals to this. So f double prime 0. Wait, not 0. E, I think. E. Okay. E. Okay. 2 ln e over e times e to the ln e. Okay. So here, I think everything will simplify. Here you have 2 ln e is 1. So this is 1. This is 1. So you have 2e over e, which is 2. Okay, that's for this question here. But we aren't required to write y from 0 to pi, right? So here, you should write down y is from 0 to pi because you will be taking the positive square root. You'll be taking the positive square root. So you need to show that which part of y you're taking. Okay, so y is from 0 to pi. Okay, so there's no question. Let me move on. Part B. So part B, we have a limit and a sum here. So here, you should know this is a Riemann sum. Must I write using FTC? Yes, you must write using FTC. Okay, yes, you must write using FTC. Very good, you right? You don't need to write the fundamental theorem of calculus. You just write 3 letters. I think quite a good deal already. Need to show 1 or 2. What do you mean? What do you mean need to show 1 or 2? FTC, no need. Left right by FTC can already. Okay. Okay, so let me go and finally do part B here. So here, you should know this is a Riemann sum. We have a limit, we have a sum, we have an infinite sum here. Most likely, it's a Riemann sum. Okay, so for Riemann sum, this is what you should know. The limit of n approaching infinity of the summation of k equals 1 to n of f of k over n times 1 over n. This is the integral, okay, of 0 to 1 fx dx. Fx dx. This is the Riemann sum formula here. Okay, you want to convert a summation to an integral, then you integrate. Okay, so again, I mentioned in the tutorial that the first step you should do, always factorize out 1 over n. Always. Okay, or bu minus a over n. Okay, or factorize out. Factorize b minus a over n, which is 1 over n in our case. Okay, always factorize out 1 over n. So my expression has n over 4 over 3. I'm going to factorize 1 over n. 1 over n. And whatever is here. So cube n plus 1 plus cube root n plus 2 until cube root n plus n over n 1 over 3. Okay, so that's the first step. Now you should be doing. Always factorize out 1 over n. Okay, the second step, okay, you try and simplify. So after you simplify, right, the second step is you want to find out number 2, find k over n. Okay, find k over n. So first, you can either combine this into a sum first. So let me just rewrite this as a sum. So this is the sum. Okay, so this is sum of k equals to 1 to n. Okay, of cube root of n plus k over n to the power 1 term. Okay, so you just check what is the term that is changing. 1, 2, up to n. So this one is okay. Just replace it by k. Okay, so next step, we want to find out where is k over n. Now k over n is still not very obvious where it is. But here, notice that this one, right, this n to the power 1 over 3, this is the cube root of n. Right, so this one I can rewrite this as a limit n approaching infinity, 1 over n, summation equal to 1 to n. Okay, this is the cube root of n plus k over the cube root of n. So this is the limit of n approaching infinity, 1 over n, summation k equals to 1. So this, you can combine these two cube roots together. Okay, n over n plus k over n. And this is equals to limit of n approaching infinity, 1 over n, summation of k equals to 1 to n, okay, the cube root, okay, of n over n is 1, and then plus k over n. And now we have my k over n already. Okay, very good. Since I have a k over n, okay, I have this k over n here, I can replace this by x. Okay, can replace it by x. So this entire thing, okay, let me put my 1 over n at the back here. So my function here, this is my function. My function here is this. Okay, so this summation and the limit will become the integral from 0 to 1, okay, of my function here, which is the cube root of 1 plus x dx. Now just go and calculate the cube root, the integral for this from 0 to 1. Here you should get 3 over 4, 1 plus x to the power of 4 over 3. So, oops, sorry for that. My app is frozen. Okay, somewhere. Okay, so we're here. So this is from 4 to 3, 4 over 3, from 0 to 1. You can just go and evaluate this. This should give you 3 over 4 of 1 plus 1 to the power 4 over 3 minus 3 over 4 of 1 plus 0 of 4 over 3. Okay, let's evaluate this. It should be done. Okay, so that's for 9b. Where are points 1 and 2? What are points 1 and 2? These are like the steps you should do. Okay, so first step is you want to factorize out 1 over n. And the second step is you try to find k over n and replace it by x. So you can see here, right, my function here. So this very complicated looking thing, you can just replace this k over n by x here. Okay, you replace by x. Then 1 over n is dx. 1 over n becomes dx. The limit and the sum will become the integral. Okay. So if it's phi n, then do we just replace phi n by n? What is phi n?
Like the n is like instead of like 2n, right? Which is like n plus n, it's like n plus 5n, something like that.
So you are going from 1 plus 2 plus 3 until 5n.
Yeah.
Then yes, it will be n, wait, until 5n. You don't replace it by k though. Let me think. You're saying this. Then you should wait. Let me think. Because this is. Then I don't think you can convert to a Riemann sum though. Up to 5n. Then you replace your summation here should be 5n here. It's not the. Your summation here should be 5n if it's 5n lah. But that doesn't really make sense also.
Oh, that, okay.
Yeah, it doesn't really make sense to do that. Usually the question would be so funny lah, because if it's 5n, right, your summation will be k from 1 to 5n. But for this one here, you cannot really convert it to a Riemann sum.
Oh, okay.
Yep. Okay.
Yeah.
What is the difference between xk and xk star? Those are your sample points for your Riemann sum. So if you look at your definition of your Riemann sum, I think the lecture notes should have it. We replace k over n by x and 1 over n by dx. Yes, that's correct. Okay. If there's no other question, let me move on to the last question. Question 10. Still got 2 more parts. Okay. So let's quickly go through this. So we want to integrate x plus 1 over x squared plus x plus 1 from 0 to 1. We'll give an answer in this form. Okay. So first thing to know, first little thing to know, when we have a fraction like this, you should try and simplify first. Is it possible for me to factorize this and divide? Unfortunately, the answer is no. So, okay, that's too bad. Next thing to check, if we try and differentiate the denominator, okay, if we try and differentiate the denominator, what do we get? So let's say fx is equal to x squared plus x plus 1 is 2x plus 1. Right? And this is very similar. This is very similar to this, right? We are just missing 1x. Okay? So what we're gonna do here is we're gonna rewrite this integral. Okay, we're gonna rewrite this integral from 0 to 1, x plus 1 over x squared plus x plus 1 dx. Okay, from 0 to 1. So we are gonna put a half outside, and so we can put a 2 here. Put 2 multiplied by everything here. Okay, so this will become 2x plus 2. Okay, the reason why I'm doing this is because I want to use this property here. Okay, so when I replace by put a half, I have this. Now all I need to do is write this in 0 to 1, 2x plus 1 over x squared plus x plus 1. Okay, so this part here, I'm going to form one fraction. The other one, you can form the other. So this one will become plus 1 over x squared plus x plus 1. Everything here times half. Okay, so now here, this first integral is very nice to calculate because this first integral, this is a nice property here. So this is when we have the integral. When we have the integral of f prime x over fx, this is equals to ln fx. Okay, very nice property, you should know. Okay, so because the derivative of the denominator is in the numerator, I can just replace it, so it will be half. Okay, so this will be ln of x squared plus x plus 1. That's it. Absolute value. Put absolute value here. Absolute value here. Then we're going to evaluate this from 0 to 1. Okay. Then the second one here, this one you have to complete the square. Okay, we have to complete the square for this one here. So plus 1 over, this will be x plus half squared. Okay, then plus 1 minus half squared. This will give me 3 over 4. So it will become 3 over 4. Okay, so this will become this. Dx, so indicating this from 0 to 1. Okay, then here, you can refer to the formula sheet down here. We are going to apply, which one is it? This one here. Okay, we see a x squared and we see a 1 here. So we just need to, it's this one. So tangent inverse 1 over x squared plus a squared, 1 over a tangent inverse x over a. So we can just apply this formula here. Okay, so I mean this and this, they're the same. Okay, anyway, applying this formula. Apply this formula here. Let's scroll up, come to this. So this will be half ln x squared plus x plus 1, 0 to 1. So applying this formula, you have plus 1 over a. So check your x, right? Okay, you check your this formula again. Let's check the formula again. This one, my a is squared. So for this one, I have 1 over x plus half squared plus 3 over 4. Remember to make it to something squared. So it'll be square root 3 over 2 squared. Okay, so let's come back to here. Plus, okay, 1 over a. So 1 over, again, this is 3 over square root 3 over 2 squared. Okay, 1 over square root 3 over 2. Okay, tangent inverse x over a. So x plus half over a. So this is square root 3 over 2. Okay. And here I can write the evaluate outside here from 0 to 1. Go and evaluate this slowly. So this one you get half times ln of 1 plus 1 plus 1, ln 3. It's ln 3 plus